Okay, so today we're going to look at some chapter 19 problems. This chapter deals with entropy, free energy, and revisits some thermodynamics. And the beginning of the chapter starts with some questions on deciding um, kind of whether entropy is increasing or decreasing for the processes that are listed below. So we want to be able to look at these different physical processes and decide whether their occurrence will increase or decrease the entropy of the universe. Okay, so we should think about a few things before we tackle the problem. Um, we'll look at two different, I guess, types of scenarios: the state changes and then the actual chemical reactions. But for our state changes, when we're moving from solid to liquid, or liquid to gas, the transition in this direction increases entropy, right? Because entropy is going to be kind of a measurement of sort of disorder. So moving from something that's in the solid state to the liquid state, it makes sense that we would consider that an increase in sort of randomness. Okay. When we're looking at chemical reactions, we will see situations where we're going from, let's say, smaller moles of a gas to a larger number. Okay, and when the transition is in this direction, that's also going to indicate an increase in entropy. And obviously the reverse of these situations would be a decrease in entropy. So keeping that in mind, we can look at the situations that were asked in the question. So the first is a transition from H2o gas to H2o liquid. Okay, like we talked about before, since gas has a greater entropy than the liquid state, this is going to indicate a decrease in entropy. Okay, and we're going to have a negative delta S value here. We have, in the second situation, solid carbon dioxide sublimes. So that's when our CO2 solid moves to CO2 gas. So movement from the solid state to the gas state indicates an increase in entropy. That's going to be a positive delta S sign, positive delta S value. Okay, for this reaction that's occurring, we're going from a reaction or a reactant side where we have 2 moles of gas. And on the product side, we see that we have 3 moles of gas. Okay, so movement in this direction, increasing the number of moles of gas from the reactant side to the product side. That indicates an increase in entropy, which is a positive delta S value. They're taking down a scaffolding in the building right next to mine, so that'll be fun background noise for this video. Question D says that water is boiling. What's the process of water boiling? We're going from a liquid state to a gas state. That's describing an increase in entropy. So we'll have a positive delta S there. Choice E, we have gaseous iodine going to solid iodine. The entropy here decreases. So we're going from the gas state to the solid state. That will be a negative delta S value. And the last example that we're going to look at is CaCO3 solid going to CaO solid plus CO2 gas. Okay, so we have solid, and we're moving over here to something that's in the solid state, but also the gas state. So we have some conversion into the gas state. That means that we have an increase in entropy and a positive delta S. Okay, so those are some good intro ones just to get us used to the idea of kind of deciding whether something is causing an increase in entropy or not. Okay, let's look at these next questions. Okay, here we're going to calculate the change in entropy that occurs in the system when 25 grams of water condenses from a gas to a liquid at the normal boiling point, 100 degrees Celsius. The delta H VAP for water is 40.7 kilojoules per mole. All right. We probably need to look at a few things before we can jump right into this problem. We're going to be focused on this relationship to answer this question. Delta S equals Q Rev over T. This is an equation that you'd find in your textbook. It's equation 19.1. Q Rev indicates the heat that's exchanged with surroundings in a reversible process. Okay, a reversible process. A reversible process, want to know all these definitions so that we all have the same vocabulary for this. A reversible process is going to be one that can reverse direction whenever a tiny change happens in some, property that's in the particular reaction or I guess whatever the process is that you're looking at. But if some tiny change occurs in one of the properties of that process, it could change direction. Okay. Your textbook gives a good example of the difference between a reversible process and one that's not reversible. Okay, using water and freezing. And I would suggest going and looking at that if you're not really sure what a reversible process is. Okay, but when we're talking about a reversible process, it's going to be one that can change direction. When a tiny change happens. It's a very basic definition of it. Okay. All of your reversible processes are in a constant state of equilibrium, and your reversible processes represent idealized conditions. Okay, so like probably not conditions that we're going to find these processes at in real life. Okay. So when we look at this Q reversible process value, that can represent different state changes. Okay, so Q rev can represent something like the enthalpy of fusion. Okay, or we're going to look at the enthalpy of vaporization in this problem. It can represent the enthalpy of condensation. Okay, but that Q rev value can represent these types of changes. Okay, so here they're telling us what the heat of vaporization for water is, and they're asking us to figure out what the entropy change would be if condensation occurs. Okay. Now, condensation, right, is when we have gas and it goes to liquid form. Okay. Vaporization is when we have liquid and it goes to gas form. Okay. So in this problem, they gave us the delta H for vaporization. Okay. Condensation process is just opposite the vaporization process. So our delta H for condensation is going to be the negative value of our delta H of vaporization. All right. Knowing all of this, I think we have about enough information to jump into actually solving this problem. All right. So we have our Q rev in this case is going to equal our delta H of condensation. And that's going to be the opposite delta H value of our heat of vaporization, which they gave us in the problem. So it'll be negative 40.7 kilojoules per mole. The temperature that they gave us was 100 degrees Celsius. We're going to convert that into Kelvin before we do this calculation. Okay. And the other thing that they told us here was that we had 25 grams of water. Okay, if you look at the delta H vaporization value, that's in terms of kilojoules per mole. We don't have a mole, we have 25 grams. So before we can finish, before we can plug a number into this value up here, we have to make sure that we're putting in the right amount of kilojoules. Okay, negative 40.7 kilojoules is when we have 1 mole. We have to figure out how many moles of the H2O we have before we can plug that in. Okay, so we have 25 grams of water. I'm going to use the molar mass of water to figure out how many moles I have. Okay, and then I can use that delta H of condensation value and say that in every 1 mole of H2O, that's going to be negative 40.7 kilojoules. So now I'm going to have a value that's specific to this amount of water. Okay, so that's the amount of kilojoules. That's going to be specific to the 25 grams of water. Now I can calculate the delta S. So the delta S is going to be, forgot that negative sign. It's going to be negative 56.465 divided by 373 0.15 Kelvin. And we're going to get negative 0.151 kilojoules per Kelvin. And you're going to see that these delta S values are usually reported in terms of joules per Kelvin. So it's probably a good idea to then convert this into joules. So in 1 kilojoule, we have 1,000 joules. So the final value would be negative 151 joules per Kelvin. You see that we have a negative delta S value, so that would indicate that our entropy was decreasing. And in this case, we were talking about a gas moving into the liquid state because we were looking at the condensation that was occurring, and that describes a decrease in entropy. So this makes sense. Okay, so now we're going to look at the same process, but for acetone instead. Okay, so let me just remind you of the question. Okay, so let's take a look at this. We have 10 grams of acetone. It's vaporizing from a liquid to a gas, so we need the actual delta H value. This time we don't have to flip it. We don't have to flip the sign on it. The temperature that we're looking at here is 56.1 degrees Celsius. And delta H is going to be 29.1 kilojoules per mole. Okay, so we can do our setup here. 273.15. Okay, we need a molar mass value for acetone. The formula for acetone is C3H6O. Okay. So we're going to convert the grams of acetone into moles using the molar mass. And then we're going to use our delta H heat of vaporization value to figure out how many kilojoules are associated with this particular amount of acetone. Not with 1 mole of acetone, but with 10 grams of it. Sorry, that was supposed to be an 8. I don't know why I wrote a 1. Okay, so we end up with 5.01 kilojoules here. Okay, so now we're going to solve for our delta S. So our Q rev in this case is going to be 5.01 kilojoules. Our T is going to be 329.25 Kelvin. And okay, we're going to get 0.0152 kilojoules per Kelvin. And then we convert that into joules. And that's going to be 15.2 joules per Kelvin. Okay, and this is a positive delta S. We're going from the liquid state to the gas state in this one, because we're vaporizing, so we would expect a positive delta S value. All right. So let's check out the next question. Okay, so the next question has 3 parts that we're going to look at. We're looking at the combustion of propane gas. We're going to calculate the entropy change in the surroundings when this reaction occurs at 25 degrees Celsius. We're going to determine the sign of the entropy change for the system and then the sign of the entropy change for the universe and decide if the reaction is spontaneous. Sounds like a lot to do, but it's all pretty straightforward. Now your textbook goes through kind of like a derivation for you of the equation that we're going to end up using to solve this problem. It starts out with your delta S equals Q rev over T. This next formula is going to look a lot like that one. When you have your Q rev, you can think of this as the Q value for your system, right? And your system is going to have the negative Q value, your surroundings. Right? Remember that back from thermochemistry, like these are going to have equal in magnitude, opposite in sign. Okay. We've also seen this, that the delta H of our surroundings is going to be equal to the negative delta H of the system. Right? This is all the same type of processes. So if we want to know what the delta S of our surroundings are, that's something that we can calculate using the negative delta H of our reaction, right? Because, you know, if you think about it over here, we used to find our delta S value, we use the Q value and we divided it by the temperature. Here I want to know the delta S, not of the reaction, but of the surroundings. So I'm going to focus here on the delta H value, the negative delta H value of my reaction, because I know that that's going to be equal in size, opposite in magnitude of my surroundings. Okay, and then I can divide that by the temperature. So that all goes back to your thermochemistry chapter, right? All ties back in. Here in this problem, they gave us a delta H of the reaction value. So that's kind of why we want to, you know, if we had a delta H value for our surroundings, that'd be fine. But we have the delta H value for our reaction because they gave that to us after the balanced equation. They told us that the delta H of the reaction is negative 2044 kilojoules. Okay. They also told us that the reaction's occurring at 25 degrees Celsius, which means that our temperature that we're going to use will be 298 Kelvin. And now we can find the delta S of the surroundings. Okay, so it'll be negative 2044 kilojoules divided by 298. Okay, so that'll be 6.86 kilojoules per Kelvin, or 6.86 times 10 to the 3 joules per Kelvin. Okay. Um, Either way, we see that the delta S of our surroundings is a positive value. Okay. So it's going to be important when we're looking at the delta S of that universe calculation later. So the delta S of our surroundings is a positive value, right? So we're going to write that up top. Part C asks us to find the entropy change for the universe. And for us to do that, we have to look at that relationship between delta S of the universe, delta S of the system, and delta S of the surroundings. Okay, so in that first calculation, we just figured out that the delta S of the surroundings is a positive value. So that was step one. Okay, step two is to figure out whether the entropy change for the system is positive or negative. Okay, and we're looking at a reaction, and we can figure out the entropy change by looking at what's happening in the reaction itself. Okay, and what did we talk about before? We talked about the number of moles of gas on the reactant side versus the product side. If I look at the moles of gas I have here, I have 1 from the propane and I have 5 here. That's 6 moles of gas. On my product side, I've got 3 moles of CO2 and 4 moles of H2O. That's 7 moles of gas. So an increase in the number of moles of gas is an increase is a increase in entropy, which is a positive delta S value. Okay, so the delta S for my system is also going to be a positive number. Okay. Now, part C asks us to figure out whether the sign of the entropy change for the universe is positive or negative. If I'm adding together two positive numbers, that means the delta S of my universe is going to be a positive number as well. And if my delta S for the universe is a positive number, then the reaction is a spontaneous one. Okay. So why don't you try this next one? Pause this video for a second, write down this problem and give this one a try and see what you come up with. Okay. We're going to go through the same process to figure out how to solve it. So let's keep track up here. Okay, we'll keep our little tally up there. So we have 2 N2 gas plus O2 gas gives us 2 N2O. And the delta H of the reaction here is going to be positive 163.2 kilojoules. The temperature is going to be 298 Kelvin again. Okay. So we can look at the balanced reaction first if we want to and figure out what the delta S value for the system is. Here we have 2 plus 1 is 3 moles of gas on our reactant side. And this converts into 2 moles of gas on the product side. Okay, so right now I'm seeing a decrease in entropy. So this would be a negative delta S value for our system. Okay. Let's check out our surroundings. We have our formula, negative delta H reaction over T. So here we have negative 163.2 kilojoules over 298 Kelvin. Okay, so we're going to end up with the delta S for our surroundings is going to be negative 0.548 kilojoules per Kelvin, or negative 548 joules per Kelvin. Either way, the delta S of our surroundings is going to be a negative value. A negative value plus a negative value means that the delta S of our universe is also going to be a negative value. Okay, and when our delta S universe is negative, the reaction is not spontaneous. All right. Okay, let's look at the next one. This is just another it's another example using that same equation that we just looked at, but we're looking for a different variable here. So here they're telling us that for the reaction, delta H is negative 107 kilojoules, and delta S for the reaction is 285 joules per Kelvin. At what temperature is the change in entropy for the reaction equal to the change in entropy for the surroundings? So we want to know what the delta S value, or when the delta S of the surroundings is going to be equal to the delta S value of our reaction. Okay. Okay, so that's going to be, use the same formula that we had before. Let me write it up here so I can save some space. The delta S for the surroundings is going to be equal to negative delta H reaction over T. Okay. Notice here, my delta S value is given in terms of joules. It's usually given in terms of joules. Delta H and delta G are usually given in terms of kilojoules. So you have to be mindful of making that switch between units before you start to calculate a problem. So you can convert either one. You can convert the kilojoules into joules, or vice versa. It doesn't really matter. I'm going to turn this into 0.285 kilojoules per Kelvin, because that seems easier than writing some exponents over here. Okay, so now I'm going to take this equation up here and I'm going to solve it for temperature. All right, so I'm going to rearrange that equation and solve it for temperature. So temperature is going to be equal to negative delta H of the reaction divided by delta S of the surroundings. Okay, so negative 107 kilojoules divided by 0.285 kilojoules per Kelvin. So the temperature that I'm looking for is going to be around 375 Kelvin. Okay. All right, let's look at the next one. Consider the reaction for the decomposition of carbon tetrachloride. They give us the delta H and the delta S values. And then they ask us to calculate the delta G at 25 degrees Celsius and figure out whether the reaction is spontaneous. Then after we do that, so part B is if the reaction is not spontaneous, figure out at what temperature it will become spontaneous. All right. All right. So what equation are we going to use for this? Well, hopefully you feel, you've gotten a few hints from the problem itself, because this problem is dealing with 3 variables: delta G, delta H, and delta S, right? So when we're dealing with all 3 variables, we probably want to hone in on this equation right here. Okay. So let's tackle part A. We're going to find the delta G value at 25 degrees Celsius. So the temperature is going to be 298 Kelvin. You should automatically get into taking the temperature value with these things and converting them right into Kelvin, because we need to be in that absolute temperature form. And then again, I would recommend when they give you a delta S value, automatically convert it into kilojoules, so that you don't get, you don't accidentally plug something into this equation in the wrong units, then get an answer that you see in a multiple choice type question, because that would be sad. So the delta H value that they're giving us is positive 95.7 kilojoules. And the delta S value they're giving us is going to be positive 0.1422 kilojoules per Kelvin. So again, I just automatically converted that into kilojoules, not even messing around there. Okay, and now I can plug this in and I can solve for delta G. Okay, that's kilojoules. So you see my kelvins are going to cancel out, and now I'm going to be subtracting 2 units that are in terms of kilojoules. Okay, so my delta G value for this reaction is positive 53.3 kilojoules. Positive delta G value means that this is not spontaneous. Okay. Now we can still use the same type of equation to figure out what temperature our delta G would become spontaneous at, right? Our delta S value here is a positive value. That means that our delta G is going to become continually more negative as we increase the temperature. So what we're going to do is figure out what's the minimum temperature above which the reaction would become spontaneous. Okay, so if we set delta G equal to 0, right? So it's positive. Once it's going to continue to decrease, the positive value is going to continue to decrease as we increase the temperature, and it's going to at some point reach 0. Then any temperature above the one that we're going to solve for now when delta G is 0, any temperature above that, our reaction will be spontaneous at that temperature. Okay. So we know that the delta H and the delta S values aren't going to change here. So we have positive 95.7 kilojoules minus our unknown temperature value times 0.1422 kilojoules per Kelvin. Okay, so I'm going to solve this algebraically. I'm going to add this term to the left side. Okay, now I get, I'm going to put a T out front there. And now I get T times 0.1422 kilojoules per Kelvin equals 95.7 kilojoules. And now I can divide both sides by the 0.1422 kilojoules per Kelvin. And I'm going to get 673 Kelvin. So this is the temperature. Above that temperature, the reaction will start to become spontaneous, because above that temperature, my delta G value will be negative. Okay, and let's look at the next one. Again, this is another good one where, I've demoed out this problem, so now maybe try this one on your own. And the temperature, 298 Kelvin again. Okay. So we want to calculate this delta G value. Our delta H is negative 137.5 kilojoules. Our T is 298. And our delta S is negative 0.1205 kilojoules per Kelvin. I forgot to put the Kelvin in there. Okay, so our Kelvins, I like to watch the units cancel out. Okay, so here we have a negative delta G value. Our reaction is spontaneous. Okay. In this case, because we have a delta H value that's negative and a delta S value that's negative, okay, we're going to end up with a situation where as the temperature increases, this term, as the temperature increases, this term is going to get larger and it's going to stay positive because, a negative and a negative is going to be a positive. So your overall delta G is going to continually get positive as that temperature value increases. Okay. So hopefully, if you look at the equation, that reasoning makes sense to you. All right. So the next question. So many of the questions in this chapter look familiar to things that we've seen before. We're just using them in a different way now. This is an example of that. Here we are asked to find the delta S for the reaction of the balanced equation, and we are given delta S values of the individual reactants and products. So the procedure here is going to look very familiar to you because we are going to, let's write out the balanced equation first. Okay. To find the delta S for this reaction, we are going to take the sum of the entropy values of the products. We're going to subtract them from the sum of the entropy values of the reactants. Okay, and we are going to include the molar coefficients in this calculation. Okay, so if we were going to write out the procedure for this, sometimes it's helpful to label these for yourself, so you remember what you're doing here. So our products in this case are going to be the NO and the H2O, and our reactants are going to be these. Okay, just because you don't want to accidentally swap them when you're, you don't want to go through all the work of the question and then have accidentally swapped the reactants and products. So here to find the delta S for our reaction, I like to bracket off the products versus the reactants here. So I'm going to take 4 times the delta S value for the NO, and I'm going to add that to 6 times the S value for the H2O. Then I'm going to subtract that from 4 times the NH3 value plus 5 times the O2 value. So we have 4 times L to 10.8. 6 times 188.8. Okay. I'm writing this out in very long form for this one so that everyone is very clear on the process that's happening here. So inside my first set of brackets, I get 1976.0 joules over Kelvin. In my second set of brackets, I get 1797.2 joules over Kelvin. When I subtract these two values, I'm going to get a positive 178.8 joules over Kelvin. Okay. Does this value make sense? It's a positive delta S value. If you look at this reaction, what do we see? We have 4 moles of gas plus 5, so that's 9 moles of gas on the reactant side. I have 4 plus 6 moles of gas, so that's 10 moles of gas on the product side. 9 moles of gas to 10 moles of gas, that's an increase in entropy, so I would expect a positive delta S value for that. All right, let's try another example. We can do like a little spoiler. I mean, when you look at this reaction, you see that we have 5 moles of gas on the reactant side and we have 4 moles of gas on the product side. So like you would think that when we finish this calculation out that we're probably going to end up with a negative delta S value. Okay, so to find our delta S, it's going to be products minus reactants. Okay, so 2 times the H2O value plus 2 times the SO2 value minus 2 times the H2S value plus 3 times the oxygen value, 205.2, so our delta S here is going to be negative 153.2 joules over Kelvin. And like we said, we expected that value to be negative because we're decreasing the moles of gas from the reactant side to the product side. All right, so oof. Next problem again. This next problem is not hard at all. It's just that when you see a question like this, you're like, man, there's a lot of steps here. And they're not hard steps, but they're a little annoying. All right, so here they're giving us the reaction of the formation of acid rain, okay? And they're asking us to calculate the delta G for the reaction by giving us the delta H and the S values, okay? So, using this process that we've just gone over with the entropy, we're reminded that we can use the balanced equation and these values, right? These values here and these values here, we can figure out what the delta H of the reaction is by doing products minus the reactants. And we can figure out what the delta S of the reaction is by doing products minus the reactants. Once we find the delta H value of the reaction and the delta S value for the reaction, and we know the temperature, then we're going to be able to use this equation to calculate the delta G of the reaction. Right, so that's going to be our process here. Not hard, but is it a little bit annoying to have to separately calculate the delta H and the delta S? Yeah, a little bit, but we'll all survive. So we're going to start out by writing the balanced equation. Okay, and then I'm going to make space up here so that when we calculate the delta H and the delta S, we can can write it down up here. And the temperature is 25 degrees Celsius. So we'll just put that into Kelvin. Okay. So start out with our delta H. That was backwards. Okay, so our product here is the SO3. So that's going to be negative 395.7, right? Because again, it's the products minus the reactants to find these values. I'll just write that down. Sum of the delta H of the products minus the sum of the delta of the heats of formation of the products, heats of formation of the reactants. Okay. So our only product here is SO3. So that's going to be negative 395.7 kilojoules minus SO2, which is negative 296.8 kilojoules plus 1/2 times 0, because the delta H for oxygen, which is an element, is going to be 0. All right, so we end up with we end up with negative 98.9 kilojoules for our delta H. We'll write that up there. Okay, now we'll do the same thing for our delta S value. So it's going to be the S of the products minus the sum of the S of the reactants. So we're going to have products 256.8 minus 248.2 plus 1/2 205.2. Notice that for the entropy values, your elements don't zero out. That only happens when you have your heats of formation or those G values. But your entropy values, they don't zero out for the elements. Okay, so the delta S for our reaction is going to be negative 94 joules per Kelvin. And right away, I'm going to convert this into kilojoules so everything's in the same units. I do not want to be putting this into the equation and not have things be in similar units. Okay. Now that I've got these values, now we can calculate delta G. Okay. So we have our delta H value, which is going to be negative 98.9 kilojoules minus 298 Kelvin times 0.0940 kilojoules per Kelvin. Oh, got my negative sign. Can't forget your negative signs. Okay, and we're going to get a delta G value of negative 70.9 kilojoules. Okay, negative 70.9 kilojoule delta G value, that is a spontaneous reaction. All right, let's practice another one of those. Okay, so same set of steps. I'm going to calculate our delta H and our delta S values first. Okay, so we're going to have our product here, NO2. I got to be careful when we have NOs and NO2s because I'll accidentally read them wrong. So that's going to be 33.2 kilojoules minus a 0 for the oxygen and one of the NOs. So it's going to be 91.3. Okay, and for delta S, we're going to have 1 million 240.1 for the SO2 minus 1/2 of 205.2 plus 210.8. And we get negative 73.3 joules over Kelvin, which we're going to turn into kilojoules. So that's going to equal negative 0.0733 kilojoules per Kelvin. All right, we have our values. Was able to save some space here, so that's cool. Didn't have to write out all the formulas as much as the last one. So now we have our delta G equals delta H minus T delta S. So our delta H value is negative 58.1 minus 298 Kelvin times 0.0733 kilojoules per Kelvin. We get a delta G for the reaction of negative 36.3 kilojoules. Again, this indicates spontaneous reaction at this temperature. Okay, so let's look at this next reaction or this next question where we're going to actually look at the previous two reactions that we just covered when we calculated the delta G. And in these cases, we're going to change the temperature and see how that affects the spontaneity. Okay. So first we have the reaction with the SO2 forming the SO3. Okay, and we want to know what the delta G of the reaction would be at 125 degrees Celsius instead of 25 degrees Celsius. Okay, now we've already calculated the delta H and the delta S previously, so we don't have to do it again. So let's list those out. Okay. And we're going to figure out whether the reaction is more or less spontaneous at this elevated temperature. Okay. And we'll just do that by comparing the G values and we'll see if it got more negative or more positive. All right. So let's convert our temperature into Kelvin. Okay. And now we can solve and we're able to do this because it turns out that As the temperature changes, while the delta G value is affected by it, um, these values are affected a little less. So that's why we can continue to use the delta H of the reaction, the delta S of the reaction. That's also why they're calling, well, why the question says that we're going to estimate the value of delta G. We're going to be able to get a value that's very close to the delta G of the reaction at this new temperature. So we have negative 98.9 kilojoules minus 398 Kelvin times 0.094 kilojoules per Kelvin. Oops, got my little negative sign in there. Okay, so we're going to end up with a delta G reaction at 125 degrees Celsius of negative 61.5 kilojoules. Okay, if we look back at the previous problem that we did with this reaction, the delta G of the reaction at 25 degrees Celsius was negative 70.9 kilojoules. Okay, so we're actually less negative here, or more positive, whichever way you want to think of it. So the fact that at this elevated temperature, we have a delta G value that's more positive means that the reaction is less spontaneous at this temperature. Okay, now we're going to look at the same question for um, our NO to NO2 reaction. Okay, but our new temperature that we're going to compare it to is going to be negative 55 degrees Celsius. I'll put it up for those of you who want to see while I copy down the info. Okay. So there's all the info that we need. We have our temperature, our new temperature in terms of Kelvin, and we're using our delta H and our delta S values from our previous calculation at 25 degrees Celsius. So yeah, I'll put these, just put a little indicator here that we were at 25 degrees Celsius when we calculated those. So our new delta G is going to be delta H And we get a delta G reaction value, in this case of negative 42.1 kilojoules at 125 degrees Celsius. Our delta G at 25 degrees Celsius was, I go back and look, was negative 36.3 kilojoules. Okay, so in this case, our delta G became more negative. So the reaction is more spontaneous at this temperature. Okay. All right. So we're going to go back to the same type of problem that we were looking at before with the delta S. But in this case, we're going to look at how to calculate delta G the same way. And I know these types of problems are tedious, but you have to be able to recognize them and then do them, right? It's the purpose of this chapter. So here we're given the reaction ozone in the lower atmosphere is a pollutant that can form by the following reaction involving the oxidation of unburned hydrocarbons. And we're going to use the standard free energies of formation, those delta GF values that are in your table in the appendix of your textbook, to determine delta G reaction for this reaction at 25 degrees Celsius. Okay, and this is going to work the same way that calculating the delta S value from the reactant and product entropy values worked. Same way that calculating delta H values from the heats of formation works. Okay, so we're going to take the, let me write down the formula. We're going to take the delta G of formation, the products, and we're going to subtract it from the delta G of formation of the reactants. And we're going to incorporate those molar coefficients into our calculation. Okay. And so again, it's products minus the reactants. We have to be very clear which is which when we're doing this calculation. You do not want to swap them out by accident. So in this case, we are going to have our products are going to be 1 carbon dioxide. So our CO2 value here is negative 394.4 kilojoules plus 2 H2o gas. And you'll notice that the states that these things are in are very important when you're looking up these values in your textbook. Looking up values for liquid gas versus, or liquid gas, liquid H2O versus gaseous H2O, you're going to find very different values. For ozones. Oop, got a little bit ahead of myself there. Okay, so these are my products, and I'm subtracting my reactants from them. So the delta G of our reaction here is going to be negative 148.3 kilojoules. Okay, the next question asks us to look at a different reaction and to use our calculation to figure out whether the reaction is spontaneous or not at standard conditions. Excuse me. Okay. So our products here are carbon dioxide and nitrogen gas. So we're going to have 2 times negative 394.4 plus 1 times 0 for the nitrogen gas minus 2 times the carbon monoxide value of negative 137.2 plus 2 times the nitrogen monoxide value of positive 87.6. Okay, and we get a delta G for this reaction of negative 689.6 kilojoules. Our delta G value is negative. This reaction is spontaneous. Our next problem we're going to look at is going to put us back in the mindset of something that is hopefully still familiar to you, Hess's law, back from our thermochemistry chapter. And in this case, we're going to be calculating the delta G for a reaction based on a series of steps. Okay, and we've done this before when we looked at Hess's law. So here we have a reaction of interest. Okay, and we want to know what the delta G of this reaction is based on these 3 reactions that, if added together in the right way, will give us back the reaction of interest. Okay, so we might have to make small modifications to each of these building block reactions in order to add them together and get our reaction of interest back out. Whatever changes we make to these building block reactions, we have to make a corresponding change to the delta G value that's associated with them. Okay. And then at the end of that process, to figure out the reaction, the delta G of the reaction of interest, we'll add together the delta G of the reactions that have made up our overall reaction. Okay. So it is good. It's a good practice to write down your reaction of interest and like box it off. So that's, your reference point for the problem. So here we're looking for the reaction to end with 3 carbons and 4 hydrogens on our reactant side. And 1 propane on the product side. Okay. So now we're going to write down, I'm going to write down the three building block reactions that we're going to use to add together to this overall reaction. And I'm just numbering them 1 to 3 so we can differentiate them. Okay. So the best way to start this, right? I like to literally find each part of my reaction of interest within the building block reactions first. Okay. So I want to locate my solid carbon. Okay. And I see it here, right? I want to locate my hydrogen gas. See it here. All right. And I want to locate my propane. And I see that right here. Okay. Now we can make changes to the building block reactions, but we cannot make a change to the overall reaction of interest. All right. So we have to make these three reactions add together to get this reaction back out by only making changes in these reactions down here. So in our reaction of interest, we see that propane, for example, is on the product side. But in reaction 1, it's a reactant. All right. So to make that match up, I'm going to have to take this reaction and I'm going to have to reverse it so that propane is listed as a product instead of a reactant. Okay, and when I've reversed this reaction, I have to change the sign of the delta G that goes along with it. Okay, you don't want to forget to do that part where you're modifying your delta G, or else it's going to skew your calculation at the end. Okay, so I'm going to I'm going to draw a line through this first reaction now because I've changed it and I don't want to confuse myself. All right, so I've rewritten it down here. Okay. The next thing I'm going to look at is, I guess I'll look at this carbon here. I see that in my reaction of interest, I have 3 carbons. Here I only have 1 carbon. So I'm going to multiply this whole reaction by 3, and I'm going to multiply the delta G by 3 so that I can make my carbon values match up. Okay. So we're going to have to take this whole thing, multiply it by 3, and this, and multiply it by 3. Okay. So let's cross out that one because we've changed it. And now when we look at our last one, we see that we have 2 hydrogens in this reaction. We need 4 hydrogens in our final reaction. So the change that we can make to this third reaction is we can multiply the entire reaction by 2. And doing that is going to leave us with 4 hydrogens. And then we'll multiply this delta H value by 2 as well. Okay. And now we're going to check our work. Okay. And I mean, when you add these 3 reactions together, okay, the purpose of doing that is to make sure that you get the reaction of interest back out. If you add these 3 things together and you don't get the reaction of interest back out, that means that you have not made all the changes that you needed to make to the delta G's that you have listed. Okay. The only way to know the delta G of this reaction is if the reactions that you're using to calculate it give you the reaction you want back out. So what we're going to do, I like to draw a line down the middle of my arrows here because I want to keep my reactants and my products separate. Any species in one of these reactions that is the same species on opposite sides of the arrows cancels out. And it cancels out in like a 1-to-1 ratio. So if I had 1 carbon dioxide here and 3 carbon dioxides here, this one would cancel out and I would have 2 left. Okay. But in this case, I have 3 on both sides. So all of the carbon dioxides are going to cancel out. Okay. I have 4 waters on my reactant side here. I have 4 on the opposite side. So all of those waters will cancel out. Now, species that are the same and are on the same side of the arrow, so in this case, these oxygens are both on the reactant side, they're additive. So 3 oxygens on this reactant plus 2 oxygens on this reactant means I have 5 oxygens on my reactant side. And that's good because I have 5 oxygens on this product, and now they can all cancel out. And what I'm left with is going to be 3 carbons, 4 hydrogens, and 1 of the propanes. And that is what I wanted. So that means that all the changes that I made are correct. And now to find the delta G of the overall reaction, I can just add these delta G values together. Okay, so I end up with an overall delta G for this reaction of negative 23 kilojoules. Okay, let's try one more of these. Okay, so here is our reaction of interest. Here are our building block reactions that we're going to use. And again, I'm going to go through the process of locating the reactants and products from my reaction of interest within the building block reactions. Okay. So I have NO as a product, and I see it here as a reactant, and I see it here as a product. NO2 as a reactant, I see it here as a product. And N2O. Okay, so see it here, it's a reactant here, and it's a reactant here as well. Okay, so the first changes that I'm going to make are going to be making sure that my reactants and products are all on the sides that I need them to be on. So I see a problem in this reaction because my NO needs to be a product, my NO2 needs to be a reactant. Okay, I can also see, and you can do this in 2 steps or in 1 step, but I only have 1 of the NO2s in my reaction of interest, and there are 2 here. So I know that I'm going to have to multiply this reaction by 1/2 to make those coefficients the same. So I guess I can say that the 2 steps that I need to do for this first reaction are that I need to reverse the reaction, and I have to have it, or I have to divide it by 2. Okay. In this second reaction, my product is on the right side, and I can't see any. I don't know whether I have to do anything with that coefficient yet, so I'm not going to touch that second reaction yet. For this third reaction, the N2O is on the correct side of the reaction. It's a reactant where it's supposed to be, but I have 2 of them and I only need 1. So I'm going to need to have this reaction as well, or divide it by 2. All right, so let me make those changes and make the changes to the delta G value as well when you're doing this. So we're going to reverse this one and divide it by 2. So that's going to leave us with NO2 as a reactant. And 1 NO and 1/2 of an O2, right? Because I'm dividing all of these coefficients by 2. Okay, and my delta G is going to become positive, and it's going to become 35.6. Okay. That second reaction, gonna leave it alone. And I'm going to have this reaction. So I'm going to divide all of these coefficients by 2. So that leaves me with 1 N2O, 1 N2, and 1/2 of an oxygen. And my delta G for this one is going to be negative 103.7. Okay, so now I'm going to look at the canceling out. All right, so I'll start with the most obvious ones first. So here I've got a nitrogen and a nitrogen. One's on the reactant side, one's on the product side. So these are going to cancel. I have an oxygen over here, a full oxygen over here, and I have 2 halves on the product side. So if I add those 2 halves together, I get 1 oxygen, and that's going to cancel out with what's on my reactant side. Okay. I have one NO gas here and two of them here. These are both on the product side, so they're going to be additive. So I'm going to end up with 3 NO gases. Then I'll have my 1 NO2 gas and my 1 N2O gas. So I have everything I'm supposed to have. That means all my changes were correct. So I can add these 3 delta G values together to find the overall delta G for the reaction. And that is going to be positive 107.1 kilojoules in this case. Okay, so it's a pretty, it's not a bad process. You just have to remind yourself of Hess's law. And then just, take care to follow the steps and don't try to skip any of the steps. Go very methodically through it. Okay. So our next question is going to look at how we can calculate delta G when we are not at standard conditions. Meaning that if you're, when we're talking about gases, our standard condition is 1 atmosphere. When we're talking about aqueous solutions, that's going to be a concentration of 1 molar. Okay, so we don't necessarily always have reactions that are occurring at those conditions. So we want to be able to calculate delta G when we have other reaction situations. Okay. So we're going to look at that here. We have let's write our reaction out. 2 NO gas plus O2 yields 2 NO2. And the delta G here is negative 71.2 kilojoules. Okay, and here we're told that the delta G, or that the pressures of these things for the NO, it's going to be 0.1 atm. For the oxygen, 0.1 atm. And for the NO2, 2 atm. All right. And we want to also figure out if the reaction is more spontaneous or less spontaneous under these conditions than at standard conditions. Okay. And they tell us that the reaction takes place at 298 Kelvin. So we want to figure this out by using our equation that relates the standard delta G value to the changes that we've made. Okay. So this term here is going to represent the changes that we're making that deviate from standard conditions. Okay, so to do this, we need to know what our Q value is, and we're going to figure that out based on these pressures. And we're going to plug in the temperature value in terms of Kelvin. Okay, so hopefully everyone still remembers how to calculate Q. Products over the reactants raised to the coefficients. So our Q value here is going to be the pressure of the NO2 squared divided by the pressure of the NO squared divided by the pressure of the oxygen. Okay, so we get 4 times 10 to the third. Okay, so now to solve for our delta G, we're going to plug in our delta G standard that we were given, negative 71.2 kilojoules. our R value, and I think I mentioned this before in the workshops for sure. I don't know if I've mentioned it here before, but in this chapter, this is a good time when you see this R value. Uh, your textbook, the author of your textbook, he presents this R value as 8.314 joules over moles times Kelvin. Okay, and that's fine. The problem is that in this chapter it comes up a lot that having this unit of joules as part of your R constant can mess up your calculations, right? Because you have these, you end up with delta G values that are in terms of kilojoules, or you're not, almost nothing is in terms of joules. So I find it easier to write a kilojoules version of this R constant and just use that instead. 8.314 times 10 to the negative 3 kilojoules over moles Kelvin. And just putting that into the equation so that you don't have to worry about converting the delta G kilojoule value into joules every time that you do this calculation. But it's your choice. So live your dream. We're just going to erase some of this. It's almost like I planned it. Okay. So there we go. Now we can calculate this. All right, so I'm going to calculate my, I'll call this like my term, my deviation term first. Okay, so this is negative 71.2 kilojoules plus this thing. Okay, so I get 20.6 kilojoules. Okay, I'm going to add these together. I get a delta G for this reaction of negative 50.7 kilojoules. My initial delta G was negative 71.2 kilojoules. So even though this is still spontaneous, it's less spontaneous than at standard conditions. Okay. All right, let's try another one out. Okay. So we know we're not at standard conditions, so we know we're going to have to use our new equation that involves Q. So we might as well solve for Q first before we do anything else, just so we have it. Remember, it's products over the reactants raised to the coefficients. but we exclude solids and pure liquids from this. And that's one good indication that we have to do that, is the fact that we didn't get any information about the solid sulfur in the problem itself, right? So we're going to take our product value here, 0.0100, and square it. And we're going to divide it by 2 squared. And then we're going to divide it by 1.50. Okay, and we get 1.67 times 10 to the negative 5. Okay. Now we can look at, we're still at 298 Kelvin, and the delta G standard here is negative 102 kilojoules. Okay. So now we have everything that we need to calculate the delta G at this particular set of conditions. Okay. So let's calculate this value out first. Okay, so we're going to get negative 102 kilojoules plus negative 27.26 kilojoules. And we get a total delta G for this, for the reaction at this set of conditions of negative 129.3 kilojoules. And if we compare that to the initial delta G of the reaction, we see that at this set of conditions, the reaction is going to be more spontaneous. All right. The last thing that we're going to look at, last type of question we're going to look at here is how we can relate the equilibrium constant back to the delta G of the reaction. Okay. And we are going to use different equation. It's a modified version of the last equation that we looked at. And if you think about the relationship between K and Q and delta G and delta G prime, or whatever you want to call it, delta G naught, this equation is derived from that. Okay. So if we know the standard delta G of a reaction, we can find its equilibrium constant. Or if we know the equilibrium constant, we can use that to find delta G of the reaction, as long as we know the temperature that the reaction's occurring at, right? Now, in the question that we're looking at now, they gave us the reaction and they gave us a set of delta G values, standard delta G of formation values, and asked us to start by calculating delta G from the delta G of formation values. And we're going to use that to figure out K. Okay, so to find our delta G of the reaction, we're going to take the delta G of the products multiplied by 2 minus the delta G of the reactants. So it's going to be 2 times 51.3 kilojoules minus 1 times 99.8 kilojoules. So the delta G for this reaction is going to be positive 2.8 kilojoules. All right. Now I'm going to use this value that I just found, and I'm going to find K, because I know that 2.8 kilojoules is going to be equal to minus R times T times the ln of K. My R value is still going to be 8.314 times 10 to the negative 3 kilojoules over moles times Kelvin. I was told at the beginning of the question that the temperature that this is occurring at is 298 Kelvin. And then I have my ln of K term. So I am going to divide both sides by this product here that I'm about to get. Okay, so this is all going to cancel out. And I'm going to end up with negative 1.13. And specifically, but units wise, this cancels out. This is technically in kilojoules per mole. So when I divide, this value is in terms of kilojoules per mole after I'm done multiplying these two terms, because the Kelvin's unit cancels out and I'm left with kilojoules per mole. So that I'm dividing kilojoules per mole over kilojoules per mole, so the units cancel out completely before I calculate for the equilibrium constant. Okay, now I'm going to raise both sides to the E, and that's going to cancel out that natural log. So my equilibrium constant here is going to be 0.32. Okay. Let's look at one more of those. I like this version of it because they're telling us a different piece of information here. They're telling us that the Kp value of the reaction we're looking at is 81.9 and asking us to find the delta G for the reaction from that. The reaction is still at 298 Kelvin. Okay, so here, to find delta G of the reaction, it's going to be negative 8.314 times 10 to the negative 3 kilojoules over moles times Kelvin times 298 Kelvin, and then the ln of 81.9. Calculator. Okay, and we get a delta G for this reaction of negative 10.9 kilojoules. Okay, and that's the main math for this chapter. Let any of us know if you have any questions about any of it.